All right, let's get started. So, hello everyone. Hope you had a nice break. Welcome to the session 4. This session focuses on cosmic reionization history and topology probed with quasars, Lyman-α emitters, and so on. Everyone, again, please write your questions on the Slack. After each talk, I try to choose popular questions first. If you find a good question, please hit your like button. All right. So the first speaker of this session is Laura Keating, who is talking about constraining the reionization history with quasar absorption lines.
Sorry, I didn't realize I was muted. Okay, let's try that again, and hopefully I'm audible this time. So thanks very much to the organizers for putting this conference together. And yet today I'm going to be telling you something about what we can learn about the history of reionization from looking at quasar absorption lines, and in particular the Lyman Alpha and Lyman-β Forest. And so the kind of first point I really want to emphasize is there's a huge amount of information that you can learn about reionization from looking at the Lyman-α Forest. And a lot of this stems from the fact that if you look at the Lyman-α Forest along two different lines of sight, so two different directions in the sky, it can look very different. So here's an example of two spectra of quasars at the same redshift. So the black and the red are just two different sight lines. And you can see along one, you see an awful lot of transmitted flux. And another is a completely dark patch for 160 megaparsecs where you see no flux at all. And you can be kind of more quantitative about this and take lots of different sight lines. And rather than talking about the mean flux, you can talk about some effective optical depth measured along some distance. But quantitatively, you get the same thing. And as you move towards higher and higher redshift, the scatter among different lines of sight increases, with some being completely dark and some showing a lot of transmitted flux. So the question is, can we learn something from this? Why do we see the scatter at all? And why does it seem to be increasing as you go to higher redshift? Well, looking just at simple photoionization equilibrium, which is a good tracer of the neutral hydrogen in the Lyman-α Forest, you can look and you can see what does this depend on. And crucially, it depends on both the temperature and the ionizing background of the IgM. And so people have worked really hard to try and come up with different models to try and understand why these quantities should be so different along different patches and what should cause these large fluctuations. And there's, as I said, lots of different models. So you could have a varying mean free path that causes fluctuations in the ionizing background or fluctuations in temperature due to patchy reionization. But in this talk, I want to tell you what a late end to reionization can do for you and hopefully convince you that it's a good match to lots of data that's out there. And so the reason that I'm quite keen on this late reionization model is we've put a lot of work into running radiative transfer simulations of reionization in large 160 megaparsec boxes with moderately high resolution, where we can self-consistently model the temperature of the IgM and the ionizing background. And if we try and look at the mean flux we get from synthetic spectra through these simulations, we find that the only way we can match the evolution of the mean flux below redshift 6 is in a model where reionization doesn't end until after redshift 5.5, and that's the blue line there. And for comparison, you can see in the orange line, that's a model where reionization ends at redshift 6, like people commonly think. And so this is a model that's about 50% ionized at redshift 7, and that's based on trying to also match CMB data. And so if we match this mean flux, we find that we naturally can reproduce the scatter along these of the opacities that it's observed along these different sight lines of the Lyman-α Forest. So in blue there is the observations that I showed earlier from Sarah Bosman, and in orange are the distribution of sight lines we get from our simulations. And you can see we get this increase in the scatter among different sight lines as we move towards higher redshift. And this is due to this late end reionization that you have these islands of neutral gas in the intergalactic medium. And obviously, if you hit one of these sight lines, you're going to have a dark patch, where if you don't intersect one of these sight lines, you're going to get a more transmissive sight line that shows a lot of flux. And the redshift where we start to see these sight lines pop up is exactly the same redshift where these these neutral islands of hydrogen are persisting down to, so kind of above redshift 5.5, we start to get these really dark sightlines. But I also mentioned that there's these really long absorption troughs in the Lyman-α Forest, 160 megaparsecs. And they show significant Lyman beta transmission, implying that the IgM along these redshifts is at least partially ionized. And we can find something very similar in our simulations, where the black line there is the Lyman alpha, completely dark, and the blue is the Lyman beta, and you can see we do get some transmission. So you can look and see what's going on. And so these are just along the sight line I showed before is the white dashed line. And I'm just showing 3 different quantities from the simulation: the neutral hydrogen fraction, the photoionization rate, and the temperature. And you can see this dark sight line is indeed coincident with some of these neutral islands, which are the red patches. But there are little holes. These, these islands aren't completely fixed. There are patchiness in it. And it's this patchiness that allows these little spikes of Lyman beta transmission to pop up. But also, like, the IgM is very complicated, and you can see we have these shadowing effects around the neutral islands, and we also get these temperature fluctuations from the different reionization redshifts. So all of the models that I introduced in the beginning are correct in some way or another. But as well as just looking kind of at these sightlines generally and saying, oh, look, we get these dark sightlines with some Lyman beta, you can also be more quantitative about this. And there was a really nice data set recently from Christina Eilers showing co-spatial measurements of the Lyman alpha and Lyman beta effective optical depth. So along the same sight line, measuring both these quantities. And I'm just showing here the data binned in 3 different redshift ranges. And it was shown in that paper that this data is challenging to match with the uniform UV models, temperature fluctuation models, and so on. But it seems that our late reionization model is actually quite a good match to the data, with most of the data points lying within the 2 sigma contours of our model, and some lying outside. But these correspond to the long dark trough that I showed before. So this is quite a rare object, and we don't actually produce that many of them in our simulations. So we get good agreement with the observations in this late reionization model as well, which is another plus, but the sample size of the observations is still relatively small. So moving forward, can we use these absorption lines to learn something more about the epoch of reionization? Because everything I've showed so far is kind of below redshift 6. So I'm showing here 2 different simulations with 2 different reionization histories. The top one shows a more extended reionization. So the universe, in that case, is about 50% ionized at redshift 8.5 or so. And the bottom one is a faster reionization, where the universe is 50% ionized at redshift 7. But crucially, both of these models have reionization ending at the same redshift. So again, just below redshift 5.5. So they both match the mean flux below redshift 6, although they're very different at higher redshifts. So you can look and see how these 2 different models compare to the existing data. So the blue here is the fast model and the orange is the extended. And the top panel is the Lyman alpha measurements and the bottom is the Lyman beta measurements that I showed previously. And you can see in both cases, the 2 models seem to agree reasonably well with the data over this redshift range, because that's how they were designed to look. What if we tried to move to higher redshift? And so these are now, again, the same 2 models, just now moving up into higher different redshift bins. So going all the way out to, above redshift 6.5. And again, the top panel is Lyman alpha and the bottom panel is Lyman beta. And you can see that as we move towards higher redshift, these 2 models start to diverge, because you're really seeing the difference in the ionization state of the gas. And it seems that although there is a difference in the Lyman alpha, most of the difference is at kind of the higher optical depth range, which will be challenging to measure because a lot of the data there is on the upper limits. But if you look at Lyman beta, you still see a larger difference even at more moderate optical depths, which should be accessible, and that's something that we could actually measure. So it seems like people should really go after these Lyman beta effective optical depths over this redshift range, because it should be really discriminating for different reionization histories. And so that's something we'd be very excited to see. So that's kind of a whirlwind tour through trying to understand the intergalactic medium in the context of this late reionization model. So the first point, which I think is probably kind of the most important, is if you want to match the mean flux in the Lyman-α Forest, you need an IgM that's still neutral below redshift 6, all the way down to about redshift 5.3 or so. And once you get that, you find that a range of other observations naturally fall out. including matching the scatter in the Lyman-α Forest, as well as its correlation with the Lyman-β Forest. And future observations of the Lyman-β Forest will place much tighter constraints on the reionization history. So thank you.
All right, thank you, Laura. So the time for questions. So there is a question from Christine McQueen. It says that the question is that what fraction of the IGM is still neutral at redshift 6 in your work?
Yeah, so it's kind of just around like 10% or so, but it's like all the voids, so the most kind of extreme areas.
Okay, all right. So next question is from Danko. He's asking, do your models prefer Finkelstein 19 versus Robertson 15 reionization history?
So I don't know that I've compared it directly against those two reionization histories, but we definitely prefer kind of, if you include trying to fit the CMB data, we prefer kind of a fast reionization that's ending late. So about 50% ionized at redshift 7 and completely ionized just below redshift 5.5.
Okay, great. And the next question is from the Melema Garelt. The question is that, what does your late reionization model imply for the changes seen in the population of LAEs around redshift 7?
Yeah, so we've looked to trying to model the LAEs and their correlation with the Lyman-α Forest, and we get great agreement there. I haven't myself looked at how the Lyman-α fraction evolves, but other people have looked at it in very similar reionization histories, actually based on these simulations, Lewis Weinberger, and he finds that kind of it's good agreement with the observations.
Okay, great. So the next question is from Brant Robertson. In the models that have different tau CMB, but similar tau Lyman alpha below redshift 6, how do their temperature histories compare?
Yeah, so the model that reionizes earlier, so that has the higher tau CMB, that's cooler just because more of the gas has cooled early or has been ionized early on, so it's had more time to cool. So there is potentially some discrimination there with if you looked at the temperature measurements as well.
Okay, great. So next question is from the Fahad one. The question is, what's the tau CMB you used in your two different models, extended versus faster?
Yeah, so the faster one has a tau CMB that's like in good agreement with Planck, so about 0.05. The more extended reionization history would be in disagreement with Planck, so it's more like 0.07 or so. But I think it's interesting to see like how well you can discriminate between these models just using the Lyman-α Forest. I think that's cool.
Okay, great, thank you. So the next question is from the Xiaohan Wu. So how plausible is it to robustly measure the Lyman-β for, Lyman-β Forest at such high Z? There must be a lot of contamination from the Lyman-α Forest.
Sure. So in all the estimates of the Lyman-β Forest I showed there, we have forward modeled that contamination. So that's all taken into account. But yeah, it is pretty substantial. And we also looked at trying to model the Lyman-γ Forest, but there the contamination is just too much. You don't get anything out.
All right. So any more questions from the audience? Yeah, if not, thank you, Laura.
Thank you.
Okay. All right, so let's move on to the next talk. So next speaker is Haruka Kusakabe. She's talking about the late or patchy reionization suggested by the LA fraction measured with HST and MUSE.
Thank you very much, Masami. Okay, I'm sharing my screen. Okay, I'm sharing my slide. Can you see my slide?
Yes.
Okay, thank you. So hello, I'm Haruka Kusakabe, a postdoc in University of Geneva, working with Anne Behame and Jeremy Blazo. I got my PhD from University of Tokyo last year and moved to Geneva and started to work with nice people here. To organizers, thank you very much for giving me an opportunity to give a talk here. And we had a lot of exciting talks in this conference, including those about H1 gas fraction in the IGM. And my talk is about LA fraction for faint galaxies in the post or end of reionization epoch. As Lola introduced, recently observation of large fluctuation of Lyman-α Forest in the spectra of high-G quasars suggest a late and or patchy reionization scenario, which has been reproduced well in simulation. Another probe of the H1 gas fraction in IGM is LA fraction. In recent studies, DeVars et al. Found a low value of LA fraction than previously reported, and it suggests more moderate or flat evolution of LA fraction, and it implies a later and or patchy reionization process. To assess the evolution of the LA fraction, or especially the drop of the LA fraction at redshift higher than 6, an accurate measurement of LA fraction at redshift lower than 6 is required. However, in the previous work, the selection of the parent sample and the measurement of Lyman-α emission are inhomogeneous over a wide redshift range. So building on previous studies, now we have been able to construct a more complete picture in UV and in Lyman-α. Therefore, in this work, using deep HST and MUSE data, we have constructed UV complete sample and homogeneously detected Lyman-α emission to assess the evolution of Lyman-α emitter fraction. First, we constructed our UV sample based on photometric redshift in the Rafalski catalog and checked the completeness in UV. These panels shows the UV magnitude distribution and the completeness limit in the previous work. The blue shades indicate a popular UV magnitude range of so-called faint sample in the pioneering work in Stout et al. Recently, Alavarro et al. And DeVars et al. Pushed the completeness limit to a faint UV magnitude. However, none of previous studies have a UV complete in this faint UV magnitude range. On the other hand, we confirmed that the UV magnitude distribution of our sample shown by this magenta line is consistent with the expectation from the luminosity function shown by the dashed black line. Our sample is complete in the blue shade and even fainter UV magnitude down to -70.75 from redshift 3 to 6. The LA fraction has been well investigated already, but this is the first work with a UV complete sample. Next, we used MUSE Hubble Ultra Deep Field survey data and detected Lyman-α emission in 1D spectra without including halo emission. We inspected all the detected sources visually. Here is an example of contaminated detection. Although we can clearly see Lyman-α in 1D spectra, it is due to a neighboring Lyman-α emitter as shown by narrowband of MUSE and HST images. So thanks to MUSE IFU data, now we have a homogeneous Lyman-α sample by excluding this contamination. Then we measured Lyman-α fluxes with asymmetric Gaussian fitting and estimated the completeness from simulations with fake Lyman-α lines. Okay, I will move on results. This plot shows the LA fraction as a function of redshift for UV complete sample down to -70.75 magnitude for strong Lyman-α emitters. The error bar is calculated from binomial proportional confidence interval, not by Poisson error. We find a low value of LA fraction, roughly 10 to 30% at redshift 3 to 6. And this low value may suggest a short duty cycle of Lyman-α emitters. We also confirm a moderate increase of LA fraction from redshift 3 to 6. Next, we compare our result with previous ones from common UV magnitude range, so-called faint sample, but brighter than the previous plot. Our LA fraction is consistent with those in the literature at redshift 4 to 5 for both weak and strong Lyman-α emitters. And we confirm that the slope extends down to redshift 3 for both samples. However, at redshift 5 to 6, we find a low value. Well, combined with the latest result, it may imply a late or patchy reionization. Next, we study the dependence of LA fraction of UV magnitude, comparing with previous results. Surprisingly, our result is consistent with no dependence of LA fraction on UV magnitude. The slope remains flat in contrast to Stark et al. It implies a weaker dependence of the intrinsic equivalent width and H1 column density or dust attenuation on UV magnitude than expected. In this plot, in particular at the faint UV magnitudes, there is a significant difference in LA fractions. The most plausible cause of the difference is an LBG selection bias discussed in DeVos et al. And Inami et al. So in this work, we estimated the effect of LBG selection bias for our sample quantitatively for the first time. First, in a radar band of LBG selection, strong Lyman-α boosts the flux, UV flux in the filter above the selection limit. It's typically more than 0.1 magnitude, like this, and it also depends on redshifts, so the effect stronger at the higher redshift. Then we estimated the completeness for galaxies without Lyman-α emission and with strong Lyman-α emission. The LBG selection bias can boost the LA fraction by a factor of 1.5 at a faint UV magnitudes close to the limit of selection signal to noise threshold. The result in Stock et al. Would be consistent with ours without this bias. We also compared our result with prediction in a semi-analytic galaxy formation model, Galaxies, et al. It is combined with 3D Lyman-α radiative transfer model in Behane et al. And we find that Galaxies with the bursty star formation model, shown by solid lines here, can reproduce our MUSE result better than the fiducial Galaxies model, shown by dashed line, in both panel of LA fraction as a function of UV magnitude and as a function of redshift. And using this bursty star formation model, we assess the effect of field-to-field variance. So we use 100 mock catalog from Galaxies with bursty star formation model, and we find that the field-to-field variance error shown here is smaller than the statistical error in the model, and also find that it's smaller than uncertainty of our MUSE result. Therefore, we conclude that field-to-field variance does not affect our result. So here I summarize this talk. We have studied the LA fraction with the with the first UV complete sample and homogeneously measure Lyman emission from redshift 3 to 6, we could go down to magnitude minus 70.75. And from our study, we have a general note for the future. It is essential to build a UV complete parent sample with a magnitude cut at the band without Lyman-α contamination in selection to avoid the LBG selection bias. It can boost the LA fraction factor 1.5 at a faint UV magnitude close to the limit of signal to noise threshold. And currently, I work on the next MUSE project. And so in this work, we focused on the relation between UV galaxies and central Lyman emission. But in my current work, we studied the relation between UV galaxies and Lyman-α halo. So we use MUSE extremely deep field data and measure Lyman-α halo fraction. So stay tuned. Thank you for listening.
All right, thank you, Haruka. So time for questions. I got the other question from Matthew Hayes. Very interesting to see such little evolution. Can you make any other evolutionary statements about the LBG sample? For example, beta slopes, presence equivalent width of other emission lines, Lyman-α spectral shapes.
That is a very interesting point. So using our sample, we can study the evolution of this UV property and Lyman-α property, but I didn't include it in this paper. And but for example, we don't see so much strong evolution of Lyman-α property, Lyman-α halo property, like in Florian's paper. But we can, especially using MXDF data, maybe we can see some details in the future. Thank you.
Right, great. So any more questions from the audience? Okay, just a quick question from me. So for your LA fraction versus magnitude, UV magnitude, in this plot, do you include the field-to-field variance errors in it?
Here, we didn't include the field-to-field variance error, but as estimated from simulation, it is not the dominant contribution, so it doesn't change a lot, even if we include the field-to-field variance to this measurement.
Okay, all right. So any more questions from the audience? Oh, yeah. I got this question from the Charlotte Mason. Impressive work to build such a complete sample. In the context of Laura Keating's talk on late reionization, given the small area of the survey, is it possible that this region is a late reionization region which would suppress Lyman-α?
Yeah, this is a very important point. Yeah, as you said, the survey field of MUSE deep field is very small. However, considering the cosmic volume and the direction, taking into account the direction of redshift and cosmic volume, is not so small. So in the simulation of cosmic variance using semi-analytic model, we use the same cosmic volume and using 100 mock catalog. And we found that it does not affect, cosmic variance does not affect our result. So we don't think that we luckily see the neutron hydrogen islands at redshift 5 in our result in statistical sense.
Okay, great. So there just a quick another question from Aaron Smith. You discussed this, but it is still a bit unclear to me. How robust is the removal of selection bias and contamination?
maybe about Lyman-α emitter selection. So for the Lyman-α fraction, we remove the contamination from neighboring sources, combine the HST image, and convert the MUSE PSF. We can obtain the mask for the object, and we also have a MUSE narrowband images, so we can estimate that we can check that where emissions comes from in the 1D spectra. So we can exclude the contamination better than previous 1D slit measurements.
All right, so maybe we should move on. So thank you, Haruka. All right, so the other next speaker is Moupiya Maji, who is talking about understanding cosmic reionization using Lyman-α emission. So once again, don't forget to write your questions on the Slack.
Thank you. Can you hear and see the slides?
Yes.
Okay. Good afternoon, everyone. And first of all, thank you to the Sazerac team for giving me a chance to present our results. And thanks for organizing such a nice conference in such a short time. So today I'm going to talk about how to infer something about cosmic reionization using Lyman-α emission. And this is a work done with collaboration of many people. I am a postdoc in University of Geneva. I work with mainly Anne Parham, who is also in Geneva. The other people, Thibaut, Jeremy, and Joachim, they work in Geneva and in University of Lyon. So this audience needs no introduction to the cosmic reionization. So here we all understand that it is important to understand the sources and the process of the reionization, but unfortunately, due to increasing IgM opacity, it is very hard or almost impossible to directly detect the ionizing photons around Z is equal to 6. So we need some indirect tracers for the ionizing radiation or the Lyman continuum emission. So in this work, I will focus on Lyman-α as that indirect tracer, although some other tracers have been discussed in literature in recent years. So in past few years, observers have seen that if we are able to measure the escape fractions of Lyman-α and the escape fraction of Lyman continuum, we see that there may be a correlation between the two. So these are all data from local Greenpeace Galaxies where it was possible to measure this quantity, the Lyman continuum. So this is an interesting correlation, and it begs the question, can we use this in the reionization era? So to answer that question, we need to know, does this correlation hold around Z is equal to 6 and higher redshifts? And does this hold for all galaxies, since we don't have a very big sample in observations yet? And then we can also ask that if it does, if there is a correlation, then given the Lyman-α properties of the galaxy, such as their escape fraction, can we then calculate Lyman continuum properties, such as Lyman continuum escape or Lyman continuum luminosity? So since these quantities are hard to actually observe in Z is equal to 6, it is a great idea to explore some results from simulations. So here we use the Sphinx simulation. And this morning, Matthew already gave a little of introduction about the Sphinx. So in very short, this is a radiation hydrodynamical simulation. It has very high spatial resolution of about 10 parsec. The box size is 10 megaparsec. It's a Ramses RT code. And the simulation runs till Z is equal to 6, and it has reionized the universe by then. So here, for doing the Lyman-α calculation, we post-process the galaxies in the Sphinx simulation using code called RASCAS. This is a new public code which is open for anyone, and I encourage you to all go and check this out. So here we take each of the galaxies and then run the radiation transfer using both recombination process and the collision process. So for each halo, we run it twice for these two processes, and we employ 10 to the power 5 photons for each. And we here consider the halos which have stellar mass more than 10 to the power 6 solar mass. So the halos in these high redshifts have complicated geometries. Here you can see one example. This is the stellar distribution, and this is the gas distribution of the same galaxy. So lots of satellites are roaming around, and interactions and often mergers also happen. So the quantities that we will describe next, these are all global quantities, and the production of the Lyman alpha and the propagation of the Lyman alpha is happening till the halo virial radius here. So we don't take into account IgM in the next results that I'm going to show. We have galaxies at different snapshots, and we tested and found that the properties of the galaxies at different redshifts, 6, 7, 8, 9, and 10, are not very, very different. They have similar in physical Lyman alpha and Lyman continuum properties. So we stacked them together to get better statistics. So in the end, our sample size is 1933 galaxies. So coming to results, the first is luminosity. The intrinsic luminosity of Lyman continuum correlates quite well with Lyman alpha, as we see here. This is a good correlation, and this is to be expected because both of them depend primarily on the star formation rate of the galaxy. And if we look at the escaping luminosity or the output luminosity for both of them, there is still a correlation, but there is a greater dispersion here, especially for the fainter galaxies. Coming to the escape fraction, we started with that observational plot of the escape fraction, and the observational plots are here in blue. So we plotted all of our galaxies here, and some of them are very faint. And we find that if we plot all 1900 galaxies, there is basically no correlation here. It is scattered everywhere, and we can in general only say that Lyman alpha escape fraction is greater than Lyman continuum escape fraction. This is the one-to-one relationship line. So we asked that, okay, what if we just took brighter galaxies? So we took, say, a cut of 10 to the power 39 arcs per second, and then we still have a very scattered relationship. But if we go towards more bright galaxies, such as greater than 10 to the power 41, it seems like there may be a correlation which matches our observations. So we think that the observed positive correlation of the two escape fractions may be a selection bias, which holds true only for the brightest galaxies. So we find that at different luminosities, galaxies can have very different escape fractions. But it is often useful to know what is a typical escape fraction or a median escape fraction. So here we divide our sample according to their Lyman alpha output luminosities. So we bin them, and in each bin we have this many galaxies. So the median, and then we plot the median value of the escape fraction of Lyman alpha and the escape fraction of Lyman continuum. And we find that in faint galaxies, both of the escape fractions are very high, basically 1. And then both of them drops. It is seen that Lyman continuum has a kind of similar escape fraction for a large range of Lyman alpha luminosity, and around 10 to the power 41, 42, which is mostly interesting for the current observational limits. The Lyman continuum escape fraction is around 10 to 15%. And for Lyman alpha, it hovers around 30% here. So this may be interesting for observers. We can also ask the question that what is the total contribution to reionization for these different groups of galaxies? So for different bins, we sum up all the Lyman continuum luminosities of all of the galaxies here, and then we plot that total output here. So we see, first of all, that this is the good statistics region. We have few galaxies here and few galaxies here. And we see that the very faint galaxies contributes less to reionization. They have very high escape fractions, yes, but they are so faint that the total number of ionizing photons that escapes these systems is not very much. And the ones that are brighter, their escape fraction is low, but their luminosity is high. So with these two, it turns out that these ones contributes more ionizing photons to reionization. So till now, I talked about the total escape fractions. So if we look at their sky maps or the helipix maps, say of two galaxies, we see that the Lyman alpha escape fraction map and the Lyman continuum escape fraction maps, they are very anisotropic. Some regions are very bright and some are quite dark. It is also seen that the places which is bright for Lyman alpha is also bright for Lyman continuum. So the escape directions of Lyman alpha and Lyman continuum seem to be highly correlated. And I think someone asked this during Matthew's talk. So yeah. So in the last part, we asked that, okay, we did not see any one-to-one easy correlation between escape fractions of Lyman alpha and Lyman continuum, but given that we have a lot of data, can we predict Lyman continuum properties given all the other galaxy properties that we have? So this part of the work is inspired by work done by Axel Ranholms and Matthew Hayes, and I think Axel is giving a talk in the next session. So here we are doing a multiple linear regression method where we, this is kind of a formula that we are trying to apply. So Y is something that we want to predict, such as Lyman continuum luminosity. And then different X are different galaxy properties that are available to us, such as their physical properties and their Lyman alpha properties. So then we try to fit such kind of relation and see if we can recover the actual values of Y. We can also then ask that if this relationship holds, then which one of the X's are most important? So here are the values that are observed in simulation. This can be called as like true values. And these are the prediction from our model. So the first, we are trying to say predict the intrinsic value of Lyman continuum luminosity. The input here are galaxy properties, that is their gas mass, stellar mass, dust mass, their sizes, stellar age, metals, and their star formation rate. So we find that the predicted value and the actual values match quite well. The R-squared is a measure of how good the model is, and if it is close to 1, that means that the model is pretty good. So we have R-squared of 0.87 here. For the escaping luminosity of Lyman continuum, we can give an input of the same galaxy properties, plus we also give Lyman alpha luminosity, and we get a R-squared of 0.80. And for the finally, for the escape fraction of Lyman continuum, we give input of the same two, plus we also give escape fractions of Lyman alpha, and we get a R-squared of 0.69 here. And then we can say that, okay, so what are the most important X variables for this? It turns out that to predict the Lyman continuum intrinsic luminosity, star formation is the most important quantity. Just the two star formation rates, the instantaneous and the long term, can explain 84% of the variance in the data. For the escaping luminosity, if we know the Lyman alpha luminosity and gas mass, it can do the job quite well. And finally, for the Lyman continuum escape fraction, knowing these three things can give us a 70% explanation of the variance. So to summarize, we need indirect threshold for Lyman continuum radiation, and we're asking if Lyman alpha would be helpful. So we analyzed 1933 galaxies, and we find that The intrinsic and escaping luminosities are well correlated for Lyman alpha and Lyman continuum. Their escape fractions are correlated, but only for brighter galaxies. And we do a multivariate regression modeling, and we find that it is possible to predict Lyman continuum given the physical and Lyman alpha properties. So Lyman alpha can be very useful to select Lyman continuum leakers. Thank you.
All right, great. Thank you, Moupiya. So time for questions. So Melema Garrett is asking that what is the physical cause of the rapid change in the median F escape Lyman continuum around a Lyman-α luminosity of 10 to the 38th arc per second?
Yeah, this I need to look into this more. These ones have very low statistics, so we can maybe ignore these ones, but yeah, I would need to look into more what happens here. Good question, thank you.
Okay, so the next question is from the Thomson. Are escape fractions related to burstiness of the galaxies? If so, do ionizing luminosities depend on the nature of the ionizing stars? BPAS model, Chabelier IMF say, thank you.
Yes, it does. Yes, it does. So I think Matthew has done more work on that aspect, and he found that yeah, the burstiness of the star formation definitely has an effect on the total Lyman continuum escape from the galaxies, and it also follows the cycle of the star formation burstiness in a given galaxy.
Okay,
so
so
yeah,
good. So the one last quick question from Matthew Hayes. What is the resolution of these simulations, especially in the CGM? And what do the Lyman alpha spectral profiles look like?
Oh, the Lyman alpha spectra, I do not have an example, but I can post on Slack one or two of them. The resolution is around 10 parsecs in the highest resolution area, and the mass resolution is 1000 solar mass for stars.
Okay, great, thank you. So time to move on. So thank you, Moupiya. So the next speaker is Fahad Nasir, who is talking about observing the tail of reionization, neutral islands in the Z=5.5 Lyman-α Forest.
Hi, anybody can see and hear me?
Yes.
Okay. So I never would have imagined that I would giving a conference talk in my jammies from the comfort of my bedroom, but here we go. So I'm Fahad Nasir. I'm going to present my work I did at UC Riverside, and the work is published, and the ARCA number you can see on your right. Okay. So the primary constraint on the redshift of reionization comes from causal microwave background. In particular, the recent PAC analysis suggests that the reionization is half complete by redshift 7.7. Of course, we know that this redshift have been moved to lower redshifts over the past 2 decades or so. So complementing constraint on the redshift reionization comes from Lyman alpha emitters and presence of damping being effects in the quasar spectra, in particular the opacity measurements in the quasar absorption line, in particular the Lyman-α Forest. So for the bulk of modeling, the assumption has been the reionization is complete by redshift 6. However, the purpose of this talk is to convince you that convince you and also explore alternative reionization scenario when the reionization is still happening and the IGM is significantly neutral at these redshifts. Here I've shown you redshift 6 quasar spectra with varying transmission in the Lyman-α highlighted in these rectangles here. So for moderate to very little transmission at the bottom sideline, the bottom sideline in particular includes the 110 megaparsec of edge, a trough. So a trough is a segment in the forest which has zero mean flux within uncertainties, of course. So any successful model of reionization has to reproduce the scatter we see from satellite to sideline and also should be able to reproduce these extreme troughs with reasonable frequency, right? So what if your working assumption is that the reionization is complete by redshift 6? So how you reproduce fluctuation you see in the forest, and your fluctuation would come from the trace neutral hydrogen left after reionization, which would be set by the photoionization rate and the recombination rate. There is significant amount of literature and try to push the limits of these parameters and try to reproduce statistical properties of the forest. So one such model I have shown here, which is given as shown as dash blue curve, we call the early reionization model, and the reionization ending around redshift 6. And we contrasted that with a model we're calling a late reionization model, the red curve here, where the reionization ending around 5.2-ish. Notice that conveniently, this model is also consistent with the recent constraint we have, Lyman-α emitters and quasar damping vanes. So how does the ionizing background should look like for the two models? So for early ionization on your right and late ionization on your left. So these are ionizing background at redshift 5.6. So for early ionization, the average, especially average mean free path, has to be significantly lower than what we expect, what we observe, what we observe at redshift 5.2. And this lower mean free path results in intensifying photoionization rate in the vicinity of sources and diminishing in the voids. Now contrast that with the late ionization model, where the fluctuation would come from the neutral islands, and therefore you don't have to assume a significant small mean free path. Notice that in the vicinity regions of these neutral islands, which are shown as white splotches here, this region would be protected from the ionizing radiation, thus producing these shedding effect. And this shedding effect is very important to reproduce the large fluctuation we see in the forest. Notice also that these cosmic void would be the last region to be ionized in both these models. In addition to fluctuation in the ionizing background, there are also fluctuation in the temperature or temperature feed in the intergalactic medium. And the reason is that it's essentially because of the patchiness of the reionization process. And we also include that in our modeling. So we'll obviously look at effective optical depth cumulative distribution function for the two models. They look very similar, extended, and also already consistent but with the observations. So here I've shown you the backend stuff again. And Lyman alpha in black curve, Lyman beta is in blue curve. And notice that there's significant transmission in the Lyman beta and coeval Lyman beta. So are we able to reproduce extreme trough in the Lyman alpha, but however have transmission in the Lyman beta for the two models? And yes, we can. So for late ionization model, the transmission in Lyman beta would come from the ionized regions in between these neutral islands. However, because of damping wing, they would offer opacity to Lyman alpha that's producing these extreme troughs. In the case of early ionization model, it is essentially the diminishing photoionization rate in the cosmic voids will produce these extreme troughs. And however, some transmission in Lyman beta. So we also looked at the trough length, the Comovi length of the troughs in our two models, and in Lyman alpha and also coeval Lyman beta bended to two redshift bands. In general, it looks like they produce very similar distributions. However, there is an axis shown as a bump here in the Lyman beta for intermediate size troughs. So trough size is from 10 to 20 megaparsec over edge, which essentially telling you the sizes of these neutral islands. So Lyman-α Forest is also sensitive to the temperature of the gas, which is responsible for the absorption, right? So this allows us to put, to measure the temperature of the intergalactic medium, and this measurement has been moved to redshift 5.8 lately by Gakwat. Notice these red points here. These are the rest point with the latest measurements. They also agree with the bump we see in the late reionization model achieved at the very end of the reionization process. The uncertainties are quite high here. So, however, future measurements, when we were able to, somebody is able to increase the sample size, we might be able to distinguish between these two models. So, how does the large-scale galaxy environment in the vicinity of the background troughs look like? So here's a background trough again. By implying the narrowband filter on Subaru Hyper subprime cam, shown as a red curve here, which sits in the middle of the background trough, George Becker was able to lay out the map of Lyman-α emitters, where colors show the magnitude in the band. Notice the deficit of Lyman-α emitters in the very vicinity of the background trough. So if you measure the Lyman-α emitters surface density in 10 megaparsec average annulus, except in the center, you arrive more quantitatively to the plot we see on your left bottom. Notice the dip in the very round of the quasar sight line is essentially telling you we're probing cosmic voids. So here the data points again, and the red curve with the shaded region represents the mean 10th and the 90th percentile of the Lyman-α surface density profile among the 100 most longest extreme troughs in our two models. And we can tell statistically we are probing cosmic voids, essentially the cosmic void that generate the most extreme troughs we see. So what about the Lyman-α surface density for the most transmittive sight lines among in the vicinity of transmittive sight lines? So we expect that for early reionization, most of the transmission would come from overdense regions, and for the late reionization model, it will come from lately ionized cosmic voids. And you might expect a tighter correlation. However, we do see a dispersion of such a correlation. This is essentially by including by the complex and contending effects of the photoionization fluctuation in the ionizing background, essentially, and temperature fluctuations. However, it seems at first glance that it's difficult to discern between these two reionization scenarios. Having said that, just the possibility of probing the large-scale galaxy environment in the vicinity of the sight line is very exciting and definitely worth further investigation, because it sheds a light on the patching of the reionization process and also on the timing. So, late reionization model can explain the observed scatter we see in the Lyman-α Forest. However, it's slightly difficult to discern with a model which is early reionization scenario, however, with a shorter mean free path. Having said that, thermal history measurements of the intergalactic medium, I mean thermal history and also temperature measurements, would play an important role in distinguishing two reionization scenarios. And in addition, direct measurement of the mean free path to the ionizing background also play an important role in distinguishing these two reionization scenarios. So if this late reionization scenario is confirmed, is very exciting time for the community, because the forest has a lot more information and we can use that to probe the tail of the reionization process. Thank you.
All right, thank you. So the time for questions. So there's a question from Tom Toms. What is the meaning of T0 at redshift z = 5 to 6 in case of the large temperature fluctuations that you showed?
What is the meaning of T0? You mean that slide? So T0 means temperature at the mean density, or this slide. Okay, maybe I think Tom is talking about this slide.
Yeah. Okay, great. So
yeah,
the next.
So these are temperature measurements of the environment. Essentially, we calculate this system analytic. semi-analytical models. So so we have an ionization field, and we use that to calculate the speed of the ionization front, which tells you what the temperature each patch is going to be ionized, and then it essentially evolves by all atomic processes we know. So these curves are calculated in that manner.
Okay, great. So the next question is from the Melema Galert. Are your MFP values in comoving or proper megaparsec?
Eco-moving, megaparsec over H.
Right. So any more questions from the audience? So I have a quick question. So
Right.
are you with a nice, LA surface density plot?
Right.
Can you show it to us? Yeah, the data points, looks like the decreasing towards 0 while your
Right.
model are, rising. So why? Yeah, I know that the shade region is allowed, but the trend look opposite.
Oh yeah, because actually these data points are from Becker, so they are the same data points. So these data points are from the Beckers, and we are probing cosmic voids. So, and we know that the extreme terms comes in the cosmic voids. That's why they're decreasing.
Right. Great. So some more questions from the audience? Okay, if not, so let's move on. Thank you, Fahad.
Thank you.
All right, so the next speaker is a Keating Doughty, who is talking about gas around galaxies during reionization. So once again, please write up your questions on the Slack.
Okay, am I audible?
Yep.
Okay, hello everyone. Oh, this is up here. Hello everyone, my name is Caitlin Doughty, and today I'm going to be really briefly talking about two different topics. So the first is the potential use of metal absorption studies to better understand the timing of reionization, in particular focusing on studies of neutral oxygen. And the second is the effects of binary stars on galaxies and gas during reionization. So measurements of the electron scattering optical depth have indicated that reionization is close to halfway finished at a redshift of 8, and measurements or inferences of the H1 neutral fraction and Lyman-α opacity suggest that it's probably finished closer to redshift of 6. However, there's difficulty in determining the H1 neutral fraction through direct measurements because of the high H1 column densities. And as has been mentioned several times already, there's evidence of substantial amounts of neutral hydrogen at lower redshifts. So clearly some lines of sight remain quite neutral even at much later times. So taking these into account, people have been interested in complementary ways of studying reionization and studying the timing of reionization. And a number of studies have suggested the use of metal absorption lines with transitions redward of the Lyman limit to better understand the ionization state of the IgM during the rapid reionization. So with this in mind, we ask, how can metals, in particular neutral oxygen, which has a very similar ionization energy to hydrogen, be used to constrain the timing of reionization? Some other uncertainties about reionization are centered on the galaxies and the stellar populations. The intrinsic emissivities of galaxies at that time are not directly observable, but are inferred from other measurements, for example, of the ultraviolet luminosity function. And this is usually used in tandem with assumptions about the stellar populations at the time. In particular, assuming that the stars are primarily single stars. Some studies of low redshift galaxies have determined that Particularly for massive stars, the majority of stars can be in binary or more stellar systems, as you can see here in these blue lines markers. So it's worth considering the possibility that epoch of reionization galaxies also contain large binary fractions. And some works, for example, at 2016, have already looked at this sort of thing, incorporating binary stars, and have found, for example, that binary stars can result in an elevated escape fraction for galaxies during reionization. So we ask here, if we assume that galaxies during that time period had a high binary fraction, what are the effects of those binary star populations on galaxies and their gas? So to address these questions, we use SPH cosmological simulations that are based on the Gadget 3 code. These simulations include on-the-fly multi-frequency radiative transfer over dozens of different frequencies. So because so many frequencies are included in the radiative transfer calculations, it can better model the photon energies that are going to affect metal transitions, which is what we're interested in. And then enrichment of the metals is modeled self-consistently according to prescriptions for evolved stars and different kinds of supernovae. And you can see these papers for more details about the simulation. So we also have interest, though, in making comparisons to observations, metal absorption studies. And so we have artificial quasar lines of sight probing the simulation volume. And from these lines of sight, we generate fake spectra using the apparent optical depth method. And this process is intended, as I said, to mimic the observational method of using quasar absorption spectra to look for the presence of metal. And these spectra have artificial noise added, and we end up with a catalog of absorption systems for a number of common metal transitions. So turning to the first topic that I mentioned earlier, keep messing this up. We examined the incidence rate of neutral oxygen absorption systems in the simulation. And you can see that here in these dashed lines. So we wanted to know, can the incidence rate of oxygen 1 tell us anything about the timing of reionization? So you can see the simulated incidence rate for weak absorption systems in oxygen 1 right here. And there's a drop in the incidence rate that corresponds pretty well with the end of the late stages of H1 reionization. And you can see here the solid line plots the H1 neutral fraction in the simulation. And the incidence rate drops when the neutral fraction is roughly 1%, which has been identified in some simulations as the epoch of overlap. So you can see that the incidence rate in the simulation occurs earlier than in these observations taken from Becker et al. 2019. The simulation may also be producing sort of an earlier reionization compared to the inferences that are coming from observations. But from this, we would say that the H1 neutral fraction volume weighted probably is reaching about 1% when you see the drop in the observations. We also wanted to see if the neutral oxygen fraction could be used to directly infer what the neutral hydrogen fraction would be. However, when we examined this, the ratio had a very scattered relationship, which didn't seem to hold much predictive power. And also wasn't as useful, perhaps observationally, because it would require photoionization modeling to determine what all of the different states of oxygen are. However, if you switch metrics and use a ratio of co-moving densities of neutral oxygen to silicon, which is another alpha element, and look at the gas in detected absorption systems, there's a very clear relationship between these two quantities. And this H1 neutral fraction in absorption systems very well matches the mass-weighted H1 neutral fraction. So if the scaling of this relationship could be better determined with modeling, this could be useful for learning more about the ionization state of hydrogen. The relationship doesn't hold as well when you're looking at basically the volume-weighted neutral hydrogen fraction. So regarding the second topic that I mentioned, I would be talking about the effects of binary stars. We run 2 different simulations with different versions of the binary population and spectral synthesis. SPS model described in Eldridge et al. 2017, and one with single stars and one with binary stars. So on the left here, you can see a spectral energy distribution of a model stellar population, one with single stars, one with binary stars. These are normalized at 1500 angstroms. And you can see that for a wavelength above the Lyman limit, the amplitudes of these are very, very similar, virtually identical. However, for lower values, the amplitude is higher for the binary star spectrum. So the spectrum is harder for a binary population. And when these models are ingested into the simulation, you see it results in an elevated photoionization rate in this top panel for the simulation containing binary stars. And it means that hydrogen reionization completes sooner by about 75 million years. And this result is qualitatively also supported by results from Rosedal 2018, who did a very similar experiment here using multi-frequency radiative transfer, although with fewer frequencies. So we then examined star formation and gas properties in the 2 simulations. So first of all, the star formation rate density in the simulation decreases when we include the binary stars. You could see it really sort of ramp up after a redshift of 6. And if we examine directly the traits in the temperatures of the CGM and the IGM, where they're defined according to some overdensity cutoffs, when we examine the temperature and the density, which are these solid lines, there's not too much difference between the 2 models, but there is an elevated temperature in the CGM gas indicated by these dashed lines in the simulation with binary stars. So it's heating up some of the gas. And then by a redshift of 5, we see that there are minor increases in the stellar and ISM metallicities in the simulation with binary stars, about 7% and 15% respectively, although the overall enriched gas mass in the binary star simulation is lower. So effectively, there's less enriched gas, but it has more metals in it. So we interpret that as that accretion is somehow being halted by the gas heating. The last thing I wanted to mention is that when we look at the metal absorption systems, they seem to jive very well with the rest of the picture that we're seeing, which is that the harder ionizing background associated with the binary stars results in fewer and weaker low ionization metal absorption systems like the O1 and silicon-2, for example, and boosts the number and abundance of high ionization metals like silicon-4 and carbon-4. So binary stars could potentially affect the observable distribution of equivalent widths in these metals. So I'm over time, so I'll just leave you with my takeaways. Thank you.
All right, thank you, Kathleen. So time for questions. Right, so there's a question from the Yongda Zhu. The question is that it is interesting that the density ratio, O1 over silicon, can linearly trace the neutral fraction near absorbers. What's the physics behind that?
Our thinking behind this, using this ratio, was that the overall justification for using O1 again in this study is that it has an identical ionization energy to the H1. And so it would be in charge exchange equilibrium with neutral hydrogen, and the neutral fractions of those 2 elements are linearly related to one another, at least for certain physical conditions. Now, as I said, this sort of deviated when we actually looked at it in a simulation, which I would anticipate means that the physical conditions weren't right for that to be true. So replacing neutral oxygen, the total neutral oxygen in basically the neutral oxygen to total oxygen fraction, the neutral fraction ratio, using silicon instead of oxygen, we chose that because it's an alpha element and that the abundance should change relatively similarly to the oxygen, so it should be produced at similar rates, relatively speaking. So that's kind of the justification for that choice.
All right. So there's another question from the Thomsons. How does the IgM temperature compare between BPAS and Hart and Maddow models?
I don't remember exactly what the Hart and Maddow models would predict for the IgM temperature. I know that because this simulation has radiative transfer, the background, in certain areas, the background ends up being harder, and in other locations, it's spatially fluctuating because of radiative transfer. But I believe that sort of thing is not supposed to, that's not really what varies the temperature at the mean density, at least that's my understanding. So I'm not 100% certain how it compares to that prediction.
Okay, all right. So are there any more questions from the audience? Okay, yeah, there's another question from Sultan Hassan. If reionization happens earlier than binary stars are increasing the ionizing photons and hence star formation rate at high redshift, and you show that binary stars suppress the star formation rate at low redshift, why would binary stars behave differently as a function of redshift?
Why would they behave differently as a function of redshift? So at least as far for regarding the star formation rate density, I hope I'm not misunderstanding your question. My interpretation of that is that the binary stars contributed to an earlier reionization, and so earlier heating of some of the gas, the IgM and also the CGM, more so the CGM, and that contributed to a reduction in accretion and possibly a reduction that the reduction in the surface formation rate was based in no longer accreting as much gas. So it's possible that maybe there would be a drop in the single star model if it went to lower redshift. I'm not 100% certain how those things are sort of connecting, but we can talk about it later.
All right, so we should move on. All right, thank you very much, Kathleen. So the next speaker is the last speaker of this session. So Aaron Smith, who is talking about pathways to self-consistent modeling of high redshift Lyman-α emitters.
Okay, yeah, thank you very much. This has been an exciting conference with the virtual format, and seeing everyone's results has been really great. I just want to mostly say that this talk is mostly some things that I've been thinking about and still very preliminary. Mostly work with collaboration with Enrico Giraldi and Ro Kanan. So we have this galactic outflow model that people have spoken about for Lyman-α emitters. So I'll just briefly review this. There's this nice cartoon on the bottom here that I stole from a talk I saw once. So essentially what happens is the Lyman alpha line, just like other lines, goes in as a Gaussian, and then is reprocessed by scattering in the ISM and CGM, and in the cartoon picture splits into a double peak because of the resonant scattering. And then we have this picture at pre-reionization epochs that the blue peak is eliminated while the red peak survives, potentially. And the way to think about this actually is that these blue photons, they'll eventually redshift into resonance in the IGM, and a single scattering can take it out of the line of sight and eliminate it. Whereas the red photons become more and more optically thin. And if you have an outflow, then this helps with this process. So although this model is quite simple, the reality is that there's 3D geometry going on here, and multi-scale, multi-physics things going on. So in order to capture this, I just put together a wish list for Lyman alpha simulations. There are many of these out there right now, but sort of this is what I'd like to see, is a proper cosmological environment. This doesn't just mean the local galaxy scale, but also from a larger scale as well. Reliable galaxy formation models that have been tested potentially down to redshift 0. Also realistic feedback. So what happens when you can't resolve scales below the simulation. Also full radiation hydrodynamics. And this is of course sort of the cutting edge of a lot of these simulations these days. And these models are also including dust, growth and destruction mechanisms as well. All right, so together, if we have this, then we can really combine the simulations and the observations to build these synergies and have a predictive model. And this, of course, I'm skimming over a lot of great work that has been done with other approaches, mostly due to the time constraint here. But I want to emphasize that, of course, these simulations do exist for a number of groups. So this is an example from the fire simulations, which is work I did with Zhengjing Ma. So this sort of illustrates kind of the morphologies of this is the same galaxy at just different redshifts, where the star formation is sort of clustered and bursty and then settles down to a more compact region. And the results from these can sort of be shown as evolution with time. And I'll just highlight a few of these, the escape fractions and the equivalent widths here. So on the left plot, we have the escape fraction and for a number of Lyman alpha relevant things here. So especially the Lyman alpha line itself, the red is up here. This is what escapes the galaxy itself, and it's quite high. This galaxy was targeted to be sort of low dust, sort of low mass, but massive enough that the starburst can really produce quite a lot of Lyman alpha emission. So then once you add an IGM model, and I'm not claiming that this is a very good approach, but you can definitely suppress this down, but you can see that fairly robustly you don't lose you don't even lose an order of magnitude in your light from these systems, at least below redshift 6 for sure. Okay, so the other point is that the equivalent widths vary across sight lines. So if you look at some directions, so in the right plot here, the very dark blue regions correspond to the cosmological filaments or the cosmic web, and this is sort of inflow blue signature, and it really suppresses the Lyman alpha flux relative to other parts. And then the red parts, these are these outflow channels where feedback is very effective at sending the gas out. And this imprints on the Lyman-α signature because these are also the pathways for escape. Okay, so now that we sort of have this this background, I've sort of been thinking about ways to make this more self-consistent to connect the galaxies and the IgM transfer as well, because there's sort of this approach of doing these separately, and I sort of personally feel that there's sort of a mismatch when you do this. And of course, learning the physics from each side is very important individually, but to really compare the statistics, we would need to connect them self-consistently. So the idea here is that we'll take sort of a large scale, large box simulation, and we can track the UV background spatially resolved from this, and then use that in another step. So the parent box informs the zoom region later on. And so we have high cadence outputs for this, which can be interpolated later on. So the second stage, of course, is to perform this Monte Carlo calculations in the zoom regions, and then you're doing all the fancy bells and whistles there, and the idea then is also that you can stitch this back together with the large box much more self-consistently, even reaching these tens of megaparsec rays away from these galaxies, including the scattering as well. So this transition region. Okay, so next is then we've seen examples of this with Moupiya's talk, where then you connect back to the parent, and you can evaluate statistics with models there. So we've come full circle with this approach. So I'll just show some efforts that we're making right now. We have we're calling these the Thiessen simulations. In the abstract, we called them Moria, but this was taken and we didn't realize. So this is run with the repo RT. You should think of this as essentially being illustrious TNG with full radiation hydrodynamics run down to at least redshift 5.5 through the completion of reionization, or if it needs to later. So I'll mention that Enrico will give a proper introduction to these simulation suite. So I won't mention too much, except that it has these dust, AGN, and all the galaxy formation model in it as well. So I'll move on to the zoom simulation side of things. So these we've been testing and sort of trying to calibrate these models a little bit more. And you can see that this is a redshift 3.5 zoom simulation. And so I'm just rotating around in for the H alpha line here, which very closely sort of captures the kinematics of the disk and the ISM. You can see that rotation and velocity gradients are apparent, but you can also see that there's quite these non-trivial spectral morphologies because it's not quite settled down in a flat, nice disk at this point. Also, another interesting thing with this type of analysis is this is performed with Monte Carlo, so the dust scattering is included, and actually the escape fractions from a dust when you include scattering are actually higher than if you don't, because the photons can scatter sort of around the dust, and this includes these nice dust models that are in these codes nowadays. Okay, so this is the same galaxy zoomed out a bit, so we can see the halo more. And then we can also see the Lyman alpha flux, the spectral profile, as you look around. And I sort of want to call your attention to like these channels where they open up. In particular, this is where the ionization, ionizing photons are clearing these channels, and you sort of transfer from this very obscured blue phase into this open red phase, where things are very bright, and actually encouragingly, the spectral line profile is quite similar in some of these directions to observations. Now these models actually need to be refined, so I'm not claiming that this is the final answer or anything like this, but we're still working on this. It's nice to see the dominant red peak, even without an IGM at all. But we have to get the computing time to run at the high resolutions that we want for this as well. And I guess I'll just mention sort of this movie that I put together is just a false color rendering of the IFU data itself. So RGB is the spectra added in color space, and then the opacity, the darkness is the flux. Okay, so with that, this pretty much finishes my talk, but I will advertise a little bit here that we have these radiative transfer tools. We've put them directly inside a repo itself as a repo MCRT, but I also have them in a standalone version of Colt that I've been using as well. So this I am hoping to release publicly if I can, find enough time to do this. But there's also some nice tools in there. For example, these adaptive convergence imaging techniques. So with that, I'll just ask if you have any questions at this point.
Great, thank you, Aaron. So time for questions. There's a question from Nick Guneding. Do we know the resolution requirements for the simulations? Since the Lyman-α opacity is so high, in principle, dust distribution on very small scales can affect the escape of Lyman-α photons.
Yes, so this is a very difficult question, and I think really the approach here is to just keep trying to go to lower to higher and higher resolution, especially to test this out in simulations that resolve out in the CGM. To get those kind of resolutions, we can only do, of course, with zooms and forced resolution and so forth. As far as the dust is concerned, most of the absorption in these dense regions does happen locally. And so this is a bit worrisome, especially if you can sort of go around these clouds with Lyman-α. So I think these convergence studies really do need to happen, but we already see actually like fairly converged results even when you get down to 10 parsec resolution, and this may be a bit deceiving, but that's where we're at right now.
Right. So the other one quick question from the Maxim Trebesh. The TNG model uses an explicit subgrid description of the IGM. Do you know how this will affect your Lyman-α calculation?
Right. So yes, the idea of this is to with these large box simulations, they of course have many pitfalls that especially this Springel-Hornquist equation of state and many other things that go into these calculations that are really just sort of they're not quite correct, but they're they're well studied and they match the low redshift observations well. So the idea is that we can make these calculations on these boxes, but really the power will come when we apply the zooms that actually come from the parent box itself. And so then in these models, then we have the Smuggle model, which is still being refined, but it's actually, they're pretty close, as you can see. So here, this is essentially equivalent to the FIRE model's approach. So most of the Lyman alpha predictions will come from here. But yes, the IGM, there may be some pitfalls that we'll have to study when we get to this. Thank you.
Well, all right, great. So there are still many good questions on the Slack, but well, it's time. So yeah, thank you, Aaron. So before we close this session, so I have two announcements. The first is you can still ask questions to the speakers on the Slack. Hope you send more questions on the Slack and the speakers answer to the questions. Second, there is an interbreak session about surviving the quarantine right after this session. You can join it if you like. All right, so enjoy the break.
So today's break session is on for graduate students specifically.
Oh, okay, thanks.